All right, let's dive right into this explainer. Welcome. Today, we're unpacking the absolute magic of the thermite reaction. This is a stunning pyrotechnic marvel of chemistry and engineering that solves some surprisingly complex industrial problems. We're going to break down the science of why it works, how it behaves, and where it's actually used out in the wild. So, let's get started. Picture this. You're miles from civilization, and you need to permanently fix and join some heavy infrastructure, like a steel railway track. Obviously, plugging in a traditional electric welding machine is completely out of the question. How on earth do you fuse massive blocks of steel together out in the middle of nowhere? Well, the answer lies in the intense chemical reaction we're looking at today.
In this explainer, we'll quickly cover 1. What is thermite? 2. The redox chemistry. 3. Heat, kinetics, and enthalpy. 4. History and ignition. And 5. Real-world applications.
So, part 1. What exactly is thermite? At its core, thermite is just a remarkably stable pyrotechnic mixture. It's basically a metal powder which acts as the fuel, usually aluminum since it's cheap and has a high boiling point, mixed with a metal oxide. Think iron 3 oxide, which is, well, essentially just rust. The wild thing here is that while it generates insane amounts of localized heat, most varieties don't actually explode. It burns fiercely, sure, but there's no detonation. If you were to set this up in a lab, you'd typically place the mixture in a crucible nestled in a bed of sand. And because it's so incredibly hard to light, you can't just toss a match at it. You need something like a magnesium fuse to safely trigger that violent reaction from a good distance. What makes this stuff so uniquely powerful? Well, it actually brings its own oxygen to the party, bound right inside that metal oxide. That means it doesn't need external air to burn. You literally can't smother it. It'll even burn furiously underwater. Plus, because it relies on solid oxygen transfer, there's almost zero gas production. No expanding gases, just extreme heat in a glowing pool of pure molten slag. Moving on to section 2, the redox chemistry. This whole thing boils down to a chemical tug-of-war based on the reactivity series of metals. On one side, we have aluminum, a highly reactive metal. On the other, iron, which is much less reactive. Because aluminum sits so much higher up on that series, it is incredibly eager to steal oxygen right away from the iron oxide. And that gives us this beautifully elegant redox equation. You take iron 3 oxide, Fe2O3, and react it with 2 aluminum atoms. During the reaction, the aluminum hogs the oxygen, meaning it gets oxidized to form aluminum oxide. The iron oxide, it loses its oxygen, so it's reduced. You end up with pure molten iron on the right side, along with aluminum oxide and a colossal release of thermal energy. So the process unfolds in 3 rapid-fire steps. Step 1, a primer hits it with extreme heat. Step 2, the redox exchange kicks in at the atomic level, ripping oxygen over to the aluminum. And step 3, this generates a massive surge of heat that completely liquefies the newly formed elemental iron. All right, section 3, heat, kinetics, and enthalpy. We're talking 2,500 degrees Celsius. That is roughly 4,500 degrees Fahrenheit. The reaction easily blasts past the melting point of iron, which sits around 1,500 degrees Celsius. The heat is so blisteringly intense that the resulting iron literally runs like water. But here's the crazy part. Let's compare thermite to something mundane, like the burning carbon charcoal on your backyard barbecue. Thermite's total enthalpy is huge, negative 850 kilojoules per mole. But look at that energy density column. Thermite releases about 4 kilojoules per gram, whereas your barbecue charcoal releases 9. Wait, what? For all its blinding ferocity, thermite actually packs less than half the energy per gram of standard carbon. So why is it so violent? The secret sauce is all in the kinetics. See, while aluminum boils at a crazy high temperature, it melts at just 660 degrees Celsius. So the moment things start heating up, the aluminum liquefies and mixes intimately with the solid iron oxide. It instantly supercharges a sluggish solid-solid reaction into a rapid liquid-solid inferno. That liquid aluminum acts as an intense oxidant, spiking the temperature way beyond the melting point of iron in seconds. Which brings us to section 4, history and ignition. We actually owe this pocket-sized volcano to a German chemist named Hans Goldschmidt, who discovered the reaction back in 1893 and successfully patented it a few years later. Funny enough, he was originally just trying to find a carbon-free way to smelt highly pure metals, but he pretty quickly realized that having a portable, intensely focused heat source was an absolute game-changer for welding. And the reason it's still so incredibly practical today is simply how safe it is to handle. Thermite is completely stable at room temperature. You could hold it in your hand safely. Try lighting it with a regular match or even a standard detonator, nothing. It absolutely refuses to ignite unless it's hit with extremely high, concentrated initial heat, like from a burning magnesium ribbon or a specialized torch, just across that massive ignition threshold. Finally, Section 5, Real-World Applications. Industrially, the Thermite reaction is an absolute lifesaver. Remember our railway track problem from the beginning? This is the fix. You pack a mold around the joint, ignite the thermite on top, and boom, pure molten iron pours directly into the gap, welding the tracks perfectly in place. Because the heat is so localized, engineers also use it to fix massive locomotive axle frames right on the spot, saving a fortune in transport costs. Plus, since it's an eco-friendly redox reaction, it's now being used to safely plug abandoned oil wells as a cleaner replacement for concrete. And, true to Goldschmidt's original vision, it's still used in processes to purify metallic ores like uranium. Of course, a reaction this intense definitely has military applications too. Because thermite burns so incredibly fast and hot, and remember, you can't just put it out with water, armed forces use it for the emergency destruction of sensitive cryptographic equipment. If capture is imminent, thermite melts right through metal casings and hard drives in seconds. It also serves as a highly effective anti-material weapon for safely disabling unexploded munitions. Now, standard iron thermite is great, but it doesn't really produce much of a flame and has a pretty tight burn radius. So the military often relies on a boosted variant called Thermate TH3. By mixing standard thermite with about 29% barium nitrate, 2% sulfur, and a tiny bit of binder, they completely supercharge the thermal effect. The barium nitrate creates a massive flame and dramatically drops the ignition temperature, making it way more effective as an incendiary tool. And honestly, that just goes to show how a classic chemical reaction keeps evolving. Right now, researchers are actually shrinking these exact same mixtures down to the nanoscale. By tweaking the particle sizes, these nanothermites give us unprecedented control over the reaction speed and energy output. It leaves us with a pretty exciting question. As we truly master the fundamental magic of the thermite reaction, what incredible new materials, aerospace structures, or advanced manufacturing frontiers are we going to conquer next? Thanks for tuning into this explainer. It's been a blast.